Good morning to all. I am Dr.B.Angelin, Assistant Professor, Department of Information Technology, working in Dr. S.N.S. Rajalakshmi College of Arts and Science. Now I am going to discuss about semaphores in operating system. Semaphores. A robust alternative to simple mutual execution is to use semaphores, which are integer variables for which only two operations are defined, the wait and signal operations. It's shown as the following. As given here, these are not atomic as written in macro codes. We define these operations, however, to be atomic, protected by hardware lock. Semaphore format wait, mutual exclusion, mutex into a critical section signals and reminder. Note that not only must the variable changing steps and be invisible, it is also necessary that for the wait operations, when the test proves false, that there be no interruptions before gets decremented. It's okay, however, for the busy loop to be interrupted when the test is true, which prevents the system from hanging forever. Semaphore properties. Simple. Works with many processes. It can have many different critical sections with different semaphores. Each critical section has unique access semaphores. It can permit multiple processes into the critical section at once if desirable. Semaphores and types of semaphores. There are mainly two types of semaphores, binary semaphores and counting semaphores. Binary semaphore, it is a special form of a semaphore used for implementing mutual exclusion. Hence, it is often called a mutex. Counting semaphores, these are used to implement bounded concurrency. Semaphores can be used to force a synchronization if the preceding process does a single at the end and the followers does wait at beginning. It is critical that these be atomic in uniprocessors. We can disable interrupts, but in multiprocessors other mechanism for atomicity are needed. Semaphores deadlock. One important problem that can arise when using semaphores to block processes awaiting for a limited resource is the problem of deadlocks, which occur when multiple processes are blocked, each waiting for a resource that can only be freed by one of the other processes, as illustrated in the following examples. Another problem to consider is that of starvation, in which one or more processes gets blocked forever and never gets changed to take their turn in the critical section. Example, in the semaphores above, we did not specify the algorithm for adding processes to the waiting queue in the semaphores. In the wait of call or selecting one to be removed from the queue in the signal of call. If the method chosen is a FIFO queue, then every process will eventually get their turn. But if a LIFO queue is implemented instead, then the first process to start a waiting could stay. The bounded buffer problem. This is a generalization of the producer-consumer problem, wherein access is controlled to a shared group of buffers of a limited size. In this solution, the two counting semaphores, full and empty, keep track of the current numbers of null and empty buffers respectively. The binary semaphores mutex controls access to the critical section. The producer and consumer processes are nearly identical. One can think of the producer as producing full buffers and the consumer producing empty buffers. The readers-writers problem. The readers-writers problem, this is the same as the producer-consumer problem, except we now can have many concurrent readers and one exclusive writer. Lockers are shared and exclusive. Two possible guidelines can be used. No reader is kept writing unless a writer holds a lock. If a writer is waiting process, no new readers gain access. Reader-writers problems. Start the process, read will do, then waiting state is called a mutex. If read a count equal to 1, then waiting First reader locks writer and reading is performed. Read count is -1. If read count is equal to 0, then signal write. Last reader frees writer do. Thank you.